Well, at the end of the day, computers are using what as their input? Really just electricity, right? Probably the only thing all of us do every day or every couple of days with our laptop or desktop or phone is either make sure it's still plugged in, or two, plug it in so as to charge it. So the only physical input to our devices these days is electricity in some form. And we don't have to get into the nuances of what electricity is, but I think it's about electrons flowing into the device so as to charge it. So it suffices for our purposes to know that there's some physical input to the device, these computers and phones that we use. But that's it. And so if we harness this electricity, maybe we can start to represent information with it. For instance, here is a light bulb, this old ghost light in the theater here that's currently off. But it has the ability to turn on. We just need to plug it in or throw on a switch. And if that's the case, what's really quite compelling about the metaphor of using lights is that right now this light bulb is currently off. But as soon as I allow electricity to flow, as by plugging it in or maybe throwing a switch, now it's, of course, on. And if I unplug it or throw the switch again, it's off. Or if I plug it back in, it's on. And the implication of this very simple idea is that we can take a physical device like a single light bulb, and by plugging it in or unplugging it, we can represent information. What did I just do? I represented the light bulb being off or on, but we can just call off and on something else. We can call them zeros and ones. And so this really is the germ of an idea that gave us computers, and with it, their use of the binary system. If at the end of the day, all they have as physical input is electricity, well, let's just use that to harness and keep track of information. Let's store a little bit of electricity when we want to represent a 1, and let's let go of that electricity in some sense when we want to represent a 0 instead. And so because the input to computers is so simple, thus gives us these zeros and ones that we now use, but we seem to have created a problem for ourselves. If we only have one light bulb or one switch, if it's off, it might be a 0. If it's on, it might be a 1. But how do I count higher than 1? That problem still fundamentally remains. Well, I could, of course, use more light bulbs. So let me ask this. If we were to use 3 light bulbs, how high could we count? So with one light bulb, we can count from 0 to 1, 2 possibilities. But with 3 light bulbs, how high could we count? Well, let me go ahead and ask this question here on the screen. In just a moment, you'll see on your side this particular question via which you can respond on your device. How high can you count with 3 light bulbs? So instead of 1, I give you 3, each of which can be on or off. How high can we perhaps count? So you'll see on the screen here, the answer is coming in. We have a lot of folks thinking 60+% that it's 8 is the highest you can count. A lot of you think it's 7, and some of you also think it might be 3 or 2. So that's actually an interesting range of answers. And let's see what might actually be the case. Well, let me cut back over to 3 actual light bulbs here, all of which are off. And most naively, I think if we were to turn these light bulbs on, if they currently represent 0, obviously I could turn 1 on, and we could call it 1. Then I could turn the second one on and call it 2. Turn on the third one, and now with all 3 on, we could say now we're representing 3. But we're not really being clever enough just yet if we're only counting as high as 3, because I'm just turning them on in this story left to right. But what if we were a little more clever? Maybe we turned them on right to left, or maybe we kind of permuted them in different directions. That is, we took into account not just how many bulbs are on or how many fingers are in the air, but rather the pattern of on and off light bulbs that we've created. So let's just count this up. So let me somewhat systematically turn some of these bulbs on here, albeit virtually. Here might be 1. Here might be 2. Here might be 3. But then we're kind of done with that story. So how might we do it a little better? Well, let's start again at 0. Here might be 1. Why don't we call this 2? Why don't we call this 3? Why don't we call this 4? Call this 5, this 6, and this 7. Now, it's fine if you didn't quite see what pattern I was following, but take my word for it that that was a unique pattern of light bulbs. 8 total times. I started it off, 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 and I ended it on, on. But along the way, there were indeed 8. But how high can I count? Well, it kind of depends on what number you start counting from. And just as we thus far have been doing, computer scientists do all the time. Computer scientists, and in turn computer programs, typically start counting from 0 just because it makes sense, because when everything is off, you might as well call that 0. So if we start counting at 0, and we have 8 possible patterns that we just saw pictorially, well, that would allow us to count as high as 7. So from 0 to 7, so 7 is the highest we can count with 3 light bulbs. So those of you who proposed that 7 was the answer, 36% of you were indeed correct. 57% of you who said 8 are correct if you assume we start counting at 1. And that's fine, but at least in the computing world now, we'll generally, by convention, start counting from 0. But you are correct to say that there's 8 such possibilities.